The keynote session 3, titled Potential of Agricultural Residues as Sustainable Resources for Civil Engineering, by Dr. NARENDRA will follow. I request all the participants to enjoy the last session, where we are going to have a good kind of thing from NARENDRA sir. Now I request Pratibha ma'am to introduce the keynote.
Dr. Reddy holds a PhD from the University of Nebraska-Lincoln, USA. His expertise is in biopolymers and biocomposites. He has published about 180 research papers, 6 books, and about 20 book chapters in this area. He has more than 11,000 citations to his credit and has been included among the top 2% researchers in polymer science by Stanford University Global Ranking in 2023. He has obtained grants from national and international funding agencies also. In 2018, he co-founded a startup by name Agringenium Innovations Private Limited, which won funding from Niti Aayog and was also awarded first prize in organic waste management in national competition conducted by Ministry of Jal Shakti, Government of India. We heartily welcome him.
For being here. I know it's lunchtime, past lunchtime, and you're more hungry for food than hungry for knowledge now. And sir also asked me to finish the talk as quickly as possible. And some of the slides, some of the information is overlapping with the previous speakers. So I'll try to finish the presentation in maximum 20 minutes. So please bear with me. So the talk I want to present is the previous speakers are mentioning, right? There are a lot of issues in terms of sustainability that we have to face in the near future. Particularly related to the resources we have, natural resources, land, water, and energy. So how do we cope with the limitations we have, but yet progress with all our needs? So before I start, I'd like to acknowledge a few of my funding agencies, our sister center for providing all the facilities to work. And many of the information I show here is not from our research. It's from the literature available on the web. So I also thank those researchers who have provided this information. This slide was already previously shared. So construction industry is one of the largest contributors to the global emissions and also is to the sustainability impacts. So how can composites answer the problem, provide solutions to the problems we are facing or that are posed to us? So if we talk about composites, right, in definition, composites are anything which have 2 or more constituents, where the property of the composite should be higher than the constituents. So why I have highlighted the properties in blue is that many of the publications of research what we do, it is not like that. They report using a composites of 2 different or 3 different materials, but none of them have properties which is above the individual material. So to call it a technically composite, the properties have to be better, so we have to be careful about that. So composites are not nothing new to us. From ages we have seen composites using in different phases throughout the civilization. From ancient ways of working and preservation of produce and many different areas, composites have been a part of our life. And in the 1930s is where composites became industrially applicable when Ford Motor Company and other automobile companies wanted to use composites in automotives. That is where the composite industry gained industrial attention. And later on, as science and technology progress, we see now composites are everywhere. Probably you will not realize, you see composites everywhere from land. There is one example where composites buildings are being built only with, there is no cement or no concrete, only composites. So on land you can see composites everywhere, and in this room also these boats what we see are also made from composites. So from land to water, in this marine structure, ships are made using composites, the piers are made using composites, and here the columns are also made in composites right now because of many advantages. So from land to water, even space, most of the aerospace components, satellites and other space objects you see are made from composites right now. Most of these are made from industrial composites, but my talk today will be mostly about biocomposites. So composites are everywhere. These are just examples to show that how composite technology can be adopted. This is one composite formation for windmills, windmill blades. So this technology is available where it is being adopted everywhere. So we were talking about the previous presentations about how buildings have to be sustainable, how we have to have a new technology. One example where concretes are used to make movable bridges. If there is a disaster, you bring a bridge which will help you to transport people or transport other resources, and don't have to worry about loss of life that much. This is one very unique concept that is coming up in the hardware office in California, where they have the entire roof made out of composites. So they want to open the roof whenever they need sunlight, and when they don't want sunlight, they're going to close the roof. This is the concept they're working on. Again, entirely made only from composite materials. So that's why I said composites are everywhere. Why we need composites? One of the major advantages, they have much better weight to strength ratio, as seen in this graph. That is a major reason why we need composites for building applications. And there are also many other advantages as well. We don't have to use cement, concrete, water. Composites probably are much more sustainable compared to the regular building materials that are being used for a long time. When you talk about composites, there are various ways of classifying composites. There are different varieties of composites. The most common one are the fiber reinforced composites. We also have ceramic matrix composites, metal matrix composites, and polymer matrix composites. Polymer matrix composites and fiber reinforced composites are typically the most common ones. In terms of, even if you go further, you can even classify the composites in terms of type of reinforcement they use, like particle reinforced, fiber reinforced, and in terms of structure, they can also be classified as laminate, sandwich panel. There are various type of composites and various different ways of classification of composites. So depending on your use, depending on application, composites can be chosen. So when we, as I said, my talk is mostly about biocomposites. So what do you mean by biocomposites? Typically, biocomposites are where at least one portion, as I said, in the composites there are two major portions, one is a matrix and one is a reinforcement. So biocomposites are defined as where at least one of the component is from a bio-based resource. In this definition term, we can classify composites as partially biodegradable or completely biodegradable. Completely biodegradable composites are where both the polymer and the matrix and the reinforcement are from renewable resources. So this is what the slide you can see here. The classification has been done, as I said in the previous slides. You can see the reinforcement will also be from renewable resource. The matrix will also be from renewable resource. And this chart here on the left side shows you the different polymers that are generally used to make the considered as a matrix. Here also we have to be careful. Some of them are biodegradable, some of them are non-biodegradable. Some of them are from renewable resource, some of them are from non-renewable resource. So as in the chart shows here, there are polymers which are petroleum based but are biodegradable. Some polymers are natural based but are still also biodegradable. So depending on what your needs are, you have to choose the polymer, the matrix and the reinforcement. And in terms of reinforcement also, you have plenty of choices. We have natural fibers, we have agriculture residues which are in much more detail. We also have man-made fibers, both natural biodegradable man-made fibers and also non-biodegradable man-made fibers, which have been extensively used in the construction industry. And also you can see at the bottom, depending on technology also, different composites can be done. So this is one overview of all the possibilities of composites. As you can see, material-wise, we have plenty of plant-based materials that can be used. Basically, although composites are contain only the reinforcement and matrix, there are many more additives also added to make the property, to improve the properties further. So these are called additives or functional additives or polymer additives. They are added to improve the flame resistance, they are added to increase the water resistance of the composites, or in some cases for specific applications also this can be added. So we have a matrix, we have a reinforcement, and we have additives also. And in terms of process, there are different processes before and after the composite is formed. Before a composite formed, if you are using natural fiber, there may have to be some pre-treatments done. And even after the composite made, we have to subject it to some chemical and physical treatments. So once that is done, there are a lot of techniques also to make a composite. Very simple is a hand layup. As you can see at the top, you have a matrix, you have a reinforcement and a matrix. You lay them together by hand. It's hand layup technique, where usually most of the epoxy-based composites are made in this way. We also have filament binding composites. We have compression molding is also very common. Likewise, we have injection molding, where two components can be blended and reinforcements can be added. Once injection molding has been done, we can again subject them to compression molding to get different components. So not only textile, as you can see here, not only civil construction, composites are everywhere, aerospace to automotive to sports, composites are used in various fields. Again, this is one more picture where you want better representation of the processes used. You can please note here one of the most common way of producing composite is by extrusion. You have injection molding. You mix the reinforcement and the matrix here. You get a pellet. Once the pellets are formed, then you take it to injection molding or a compression molding again and obtain whatever shape you want. You can see a shape, the shape of the composite you want will depend on the mold what you have. So these are all the different aspects of composites. So why we need sustainable resources and what are the advantages of using sustainable resources for composites? Right. So this is right now where we are. As I said, composites and biocomposites in particular have been used from long time. So initially we were only thinking of containers and small packaging materials. Right now we have moved up to automotive parts and construction materials. But going further, there is a lot of scope for biocomposites use, especially in the construction industry. So that is where we are looking into more detail so that we will promote sustainable aspects that we have been discussing from this morning. In terms of renewable resources that are being commonly used for composite construction, as I told you, there are two major components, reinforcement and the matrix. Reinforcement, we can use the natural fibers. Madam was talking about using coil. In addition to coil, there are a lot of biofibers. Hemp, jute, scissor are all fibers that are being used. And chitosan is a material that we obtain from seashells, sea animals. Of course, wool and silk are animal sources. And so there is no limitation of any raw material. But one aspect that we have to note is that the biofibers what mentioned here, like the hemp, jute and scissor, there are specific fibers, or the dedicated fibers which have to be grown. So if you want jute, you want scissor or you want hemp, you have to grow them. You have to have land, water, all the resources required to grow the fiber. So, but still they are very much biodegradable. That is why they are called biofibers. Talk in terms of the matrix, we have both synthetic matrix and biodegradable matrix. The top one in the yellow are all biodegradable matrices. Polylactic acid is a synthetic polymer, but still manufactured using cornstarch, primarily cornstarch, but it is biodegradable. PHPV, PBS are all polymers, biodegradable polymers, but made from natural resources. But polypropylene and polyethylene, which are more commonly in the market for composites, these are from synthetic sources, but they are non-biodegradable. So you can combine any of these natural material with a natural polymer, or you can combine them with a non-biodegradable polymer. If you combine both as the natural materials, you get a completely biodegradable composite. If you use only one of them, you get a partially degradable composite. So that is what the example here. And as Madam was mentioning, we have glassware and other things also you can combine with the matrix to get the composites of your choice. So you see, as I told you, if you go for biocomposites and you talk about natural fibers, you have to grow the fiber, you need land, water and other things. Is there any alternative? As in the previous talk, they were mentioning there is no soil enough, organic soil enough, fertile soil to grow crops. So what do we do about it? So I always put this slide up and I want to highlight the issue here. I see a major problem here. The problem what I notice here is that if you see a corn crop which grows about 7 to 8 feet in height and it takes about 3 to 4 months to grow, right? Once you are harvesting the crop, we are taking only the husk and the corn out from the field. And from the husk we are only removing the cob as a byproduct and we are only collecting the seed. So effectively what we are doing is we are utilizing only about 10% of the crop we have produced. So what are we doing with the remaining 90%? Right? We are usually using a scatter field or burning the residue. So this is where I see the opportunity, where I believe instead of treating this as a residue or a byproduct, this should be a main product. Because without the stem and the stalk and the leaf, you cannot get your produce. So this has to grow. You will get the residues, but how do you use the residues is the major question. Not only for corn, you take rice, you take wheat, any major agriculture crop, you will have the residues, right? So one more classical example, you want one glass of sugar cane, you get maybe 5 to 10 times the weight in the bagasse. And a lot of bagasse is discarded right now, although some of it is used as a fuel for steam boilers in the sugarcane factories. But there is plenty available for us, a lot of residue available. And generally this is one of the issues we have. We have about 500, Madam was also mentioning, more than 500 million tons of the residue generated just in India every year. As I said, this is you can't avoid. It will be generated, but most of it is right now burnt and buried. And this is not only an economic loss to the farmers, but it's a major environmental and health hazard also. You see every year there are so many issues happening in Delhi, pollution happening because of the crop burning. So this is inevitably available to us. So India is one of the major agriculture country, and we have a lot of residue available to us if you want to go ahead and use that. So where are all the biocomposites can be used in civil engineering? You can see here most of the places. You can use it in the roof, you can use it in the walls, you can use it for prefabrication or post-fabrication. So there are a lot of areas where biocomposites can be used in civil engineering applications. But one of the major constraints of using the natural or biocomposites is the performance properties. Will we be able to meet the properties that we require for building and construction? But that all depends on how you analyze the material and what all properties you are looking for. As you can see here, the fiber properties, the way you make the composites, way you analyze the composites are all very crucial. So depending on all these factors, we can certainly develop a composite which will meet or exceed the targets of the biocomposites you want to manufacture. So I'll give some examples where the biocomposites are already being used in practice. So this is biocomposites made from rice residue. So once you grow rice, there are two major residues here. One is the straw and one is the husk. Straw is what is available in the field, and the husk is what you have to remove when you are processing the rice paddy into your rice. So there are commercial examples of where rice straw has been made into particle boards, straw bale, roofs, and even cement bonded boards. So these are all practically available in various places across the world. And in terms, when we talk about rice husk has been mixed with cement to reinforce cement to some extent, and also gypsum. These are all gypsum boards, right? So instead of using gypsum completely, rice husk has been used to combine with gypsum and make false roofings. As you can see here, this is an example of where they developed rice husk based gypsum and rice husk based false ceiling tile. This will show an example where we have also worked on a similar concept. So again, these are examples where rice straw particle boards have been made, and these are for partition walls. May not be suitable for outside walls, but interior walls certainly can be done. It's not just reducing a residue; they have very good properties also. Some of the residues, like the protein residues, what we have in nature, sheep wool, they have very good thermal insulation and flame resistance property. Now, if you are making a wall out of sheep wool or chicken feather, it will give very good sound and thermal insulation. So that will again help you to reduce your heating cost, thermal cost, and also have sound barriers. These are all the possibilities there. But as listed here, good sound absorption is possible. But right now, people are making these composite rice straw particle boards using urea and formaldehyde, which are not very eco-friendly. So we have to develop methods of developing biodegradable resins, which you can combine with the residue and make boards instead of using the urea formaldehyde resins. This is one more example which is in practical use right now, where they have combined rice straw and with a biodegradable binder, that is PHBB or PLA, and they have made bricks. So it's a self-assembling bricks. So you can use them to make build a building. So this is made from rice straw and a biodegradable material. They are claiming the mechanical strengths are all good, but the cost-wise and the performance-wise has to be answered. It is still probably the questions that needs to be answered now. And previously there was a discussion of using coir for concrete. Not only coir, hemp is grown extensively in the European countries. In India, coir is available. So hemp is cannabis where many countries have banned it. Now they are finding very, very attractive. So hemp has very excellent properties. It's one of the best natural fiber in terms of strength and stability. That is why they want to use hemp. And also because European countries have a lot of hemp grown. So this is a building entirely built using hemp plus lime. So that is one sustainable way. But how do you protect it from the natural environment? I'm not very sure. You have to have protection. Otherwise, natural fibers will degrade. They are susceptible to degradation. So you have to have external protection to the entire building. But most of the building is built using natural fiber and a natural material. And this is also very interesting what I found here. Not only the hemp or sugarcane bagasse, which I mentioned, is one of the major byproduct. This has also been used with biodegradable binders. They call it sugarcrete, And so you can see the pictures here. They made the sugar crate and then assembled into different forms. And using this, they are building sustainable materials and sustainable buildings. So that is what is being reported right now. How to use agriculture residue and make the construction and building very sustainable. But previously also I mentioned there are a lot of performance parameters that have to be answered. A lot of questions are there rather than answers. So if we are able to answer all these questions, it's only when we can claim to be really using the agriculture residues for civil engineering applications. So one of the major limitations is the poor mechanical properties so far. We also have one major issue is that server asking, is it possible to get, you are saying that it is not possible to get consistent textile fiber. That is, I'm sure you can get a man-made fiber which is consistent from manufacturers, but certainly not the natural fiber. There are a lot of processing raw material variability. So those have to be answered. Batch-to-batch variations will be there. How do you account for that? And with being natural materials, they are prone to microbial degradation or environmental degradation. So that question also has to be answered. How do you protect them from natural environment? And again, cost-wise, we are not very sure whether really the cost will be beneficial compared to the existing materials. But there are ways to improve the properties. This one, just an example of showing how we can improve the properties of biocomposites. Because when you use a synthetic polymer and a bio-based material, they are all by nature one is hydrophilic and one is hydrophobic, so the compatibility will not be there. So by simple using compatibilizers and additives which I mentioned earlier, we can improve the property of the biocomposites. So it can be done, and there are ways of improving the properties and achieving the targets. So this is what the potential of biocomposites. Some more examples of very unique way of developing sustainable materials. This is one practical example where they are developing self-healing concrete. How they do it is when they are developing a concrete, they are using a bacteria along with the concrete. So once the building or a structure is made, the bacteria, if a crack happens, if there is a crack in the concrete, moisture and other moisture will go through, and the bacteria needs the moisture for it to replicate and produce silica or calcium or lime and other substances depending on what bacteria you use. So once there is a crack and oxygen and water are available, the bacteria grows and produces and it can self-heal the concrete. So this is actually a practical application where they are showing that depending on what type of bacteria you use, the concrete can be self-healed. I'm not going to talk about hempcrete and sugarcrete, but it's also very interesting where they usually, I don't know how they get the Martian soil. So they get Martian soil, or the soil that's supposed to be mimicking in the Martian environment. That they combine with potato starch or some other biodegradable material, and they claim to have developed as good a material which is suitable for use in not only in land and even in Mars. So that's why they call it the Starkit based on the Star Wars phenomena. So they claim it to be material stronger than concrete. So these are all happening. So now there is nothing which is non-biodegradable. Everything is biodegradable here, and everything is sustainable. This is also very interesting. We also had experience of some young entrepreneurs here coming and wanted to test this kind of cement and building materials. Building materials here. What they've done is they take mycelium, which is nothing but mushroom, one kind of fungus what we have, and depending on the structure, they make a base. On the base, they put the mycelium fungus, and the fungus grows in the shape what you have predetermined shape. So you can see here they made bricks out of the mycelium, the mushroom, and then they cut out the bricks, and once the bricks are available, you can build buildings out of that. It is not just fantasy. You can see here they have made an entire building using mushroom bricks. So there is nothing non-biodegradable here. But as I said, there are limitations. I don't know how water resistant and environmental degradation resistance they have, but practically is something that is being practically implemented where you take a residue, agriculture residue like sugarcane waste or rice straw, and put some fungus on that. You cultivate and it becomes a bricks. You can practically use it in a very sustainable manner. This is what I said. What other people have done. We also work on sustainable composites using bio-based resources. In the next few slides, I will show what work we have been doing here. This is the overall depiction of what work we do here. So in our lab, we use agriculture residues and convert them into various products. One of the major products what we do is These are false ceiling tiles. As I said, gypsum-based tiles are non-biodegradable, non-renewable. So we use any different type of agricultural residues. These are sugarcane bagasse, these are groundnut shell, and this is jute fiber. And we make replacement tiles for bagasse. You can come to a lab down, you have replaced the entire lab with the gypsum-based tiles. So this is again we use both biodegradable and non-biodegradable binders here. And not only we don't have any restriction of the raw material. As you can see, we can use bagasse, we can use any grass that is grown outside, groundnut shell and rices. We have mulberry stems, we have coffeeas, we have sheep wood, which is a very unique resource because of the thermal insulation, heat insulation property. So all this we have used and we have different studies done. And as you can see here, this is a comparison we do with the normal gypsum board, whatever commercially available. And depending on the raw material and what extent we use the raw material, we can satisfy all the requirements: mechanical property, thermal conductivity, sound absorption, water absorption. And we also have the flame resistance. We have the flame resistance values also, which we can all satisfy with respect to your gypsum boards. In case there is the requirement is not satisfied, we can add some additives and definitely meet the requirements. So what I want to emphasize is there are plenty of agricultural residues where we can use and work on to develop sustainable materials. And in our case, we have only focused on the gypsum tiles. And this incidentally is the sheep wool project is one where we did with Indo-France, because in France sheep wool you can't dispose the sheep wool in the soil, or you can't burn them. So you have to use them for some of there is no use actually. So we did a project with Indo-France funding, where we use sheep wool and demonstrated that it can be as good insulation material. We can use it for gypsum, or we can use it both for side panels. So this is one approach where you can, if you want to improve the properties, very simple. You use some compatibilizer or use a flame retardant chemical, and you can use the process what we follow is very not so sophisticated at all, because we want to keep the cost simple. And one more point I want to emphasize is that so far we are not treating our raw material. Whatever agricultural residue we get use it in raw form, so that we can maintain the cost at a low level, and also have the inherent property of the raw material. If you treat agricultural residue, many cases we lose the inherent property. So retain the inherent property, we don't treat the raw material, and we use this thing. We also had a project where we used waste plastic, which is discarded, and also rubber from automotive tires. So we have combined the waste plastic and automotive tire rubber and made composites for pavement blocks. So these are pavement blocks which have been made using. Again, rubber is again non-disposable, non-biodegradable material available in large quantities, automotive tires after their use. So it can be reused in this way. That's what you have done. And so again, this is again examples of how biodegradable material are already in the market. So this is again one initiative in Europe where they want to use the entirely build the buildings only in sustainable materials without based on biocomposites. So as I said, biocomposite is not very new. The example they are showing is how they have made agro-based residue, but you go back to our history, right? Even mostly in India, you can see in the picture below here, probably everything is biodegradable here, and everything was made from natural resources available to them. I don't think there is any. So we are going back in time so that we are replicating the what was practiced long time ago to make it more sustainable engineering. This we have seen we have gone so far. So what is the future? Is there future in biocomposites, or where do we go next? So there are plenty of scopes to do. This is one example where in Zimbabwe, this is a very unique aspect. You see these are ant hills. Two aspects actually. One is this ant hill is only made from mud. If you take the mud and put in water, usually you will get dispersed, right? But this ant hills, they can resist in water for 30-40 years. They resist rain and everything. So how is it made? That is because of a glue. So more interestingly, what researchers have found is if you set the area around the ant hill in a fire and measure the temperature inside, they measured that the temperature is almost constant, irrespective of the temperature here. Also, temperature here goes much higher than ambient, but inside temperature is maintained. So based on this concept, designed buildings here where automatic airflow happens and you never need air conditioning. This has been practically implemented. This bio-inspired engineering, which is helpful for us to design sustainable materials. This is an ant which builds a nest like this, but if you typically look into ant, if you look at the ant, it only looks like a piece of paper to us. But if you look in a microscope, these are all made from nano materials. They are all proteins. So there is nanoscale engineering at work in nature. So can we replicate this to make buildings better? This again is one example where we have not realized all these years that how usually if you look at materials, right? If a material is very stiff, it has strength. If the strength and stiffness will be in opposite direction. But here you can see elephant trunk is very strong, at the time very flexible. Now there are engineering companies which are designing materials or structures where we can replicate something like elephant trunk. You get the strength and also the flexibility. And one more very interesting aspect what we have also been trying to find out so far not very successfully is if you look at turtle shell, a turtle lives in water for more than 130 years. But the composition of turtle shell is only natural polymers. There is no synthetic polymer here. But if I take the same natural polymers and try to put it, assemble it in a lab, it's not stable and you don't even get half of the strength of the turtle. So how does in nature, how is it made in such a way that it's water resistant, it is biodegradable and is very, very, very strong. If you can understand this aspect, I think it will help us a lot in building sustainable materials for the future. So in conclusion, there is unlimited scope for composites in the construction industry, but certainly we have to look at sustainable green materials. And in my view, agriculture residues is where there is a future, and to improve the sustainability aspect much further, but very much more research and development is necessary for us to go forward in this area. And in the future, I think, as the madam was mentioning, 3D printing and even 4D printing, what they're calling now, is what will take the future into very sustainable aspects. So this is all I wanted to share. Thank you very much.
Thank you, sir. Any queries? Thank you. It was actually a good session where it was something related to soil, creek, etc. rather from the regular concrete. So I once again thank Dr. Narendra Reddy to sharing his valuable time as well as the knowledge for this particular session. Now I request Dr. Prabhanjan sir to felicitate Dr. Narendra Reddy.